Thank you. And my name is Satoru Oishi, and team leader of computational disaster mitigation and reduction research team in R-CCS RIKEN. And today I would like to talk about the deep learning from SIME-related data for flood and debris flow mapping. So Professor Miyoshi gave a meteorological part of the similar aspects of our usage of supercomputer Fugaku, and then I'm talking about the hydrological approach as well. This photo shows that debris flow happened in 2017 and 2018 in Japan. The left-hand side shows the debris flow happened in northern Kyushu case. The Kyushu is very vulnerable about the torrential rain, and they suffer from such kind of debris flow flooding frequently, not only once at 10 years, but also the once at 2 years may happen. And so these kinds of debris flow devastate the buildings and the houses, and many people passed away by such kind of debris flow. And that kind of debris flow not happened in just a mountainous area like that. In the right-hand side of the figure shows that that kind of debris flow happened in the alluvial fan, I mean the normal plain of our living town. And this is the similar case in 2020 in Japan. That photo, in that photo, inside the town, lots of mud remains after the disaster happened. So all the houses are covered by mud, and then they are very difficult to remove this mud. Therefore, the disaster countermeasures has to understand the amount of the mud remaining in the town. So this is our principal target. We are using the hydrological simulation. Hydrological cycle is the cycle of the water. Water evaporates from the ocean and may form the clouds, and it happens precipitation sometimes. Then that water come into the river by slope, and part of the water went into the penetration to the ground to become groundwater. So we call them as a hydrological simulation, but basically hydrological simulation shows the from precipitation. So I mean the precipitation is given by radar or ground observation. Then they calculate the water run into the slope, then get into the river and go through the ocean. So that is a hydrological simulation. Basically, hydrological simulation uses such kind of equation. We call them as the depth averaged Navier-Stokes equation. So H shows the water depth, and UH shows the flux to X direction. VH is as well. And so du dt shows the acceleration, and this dE dx and dE df dy shows advection terms, and S shows the diffusion terms. So basically, normal hydrological simulation consists of such black figures. So they do not have these blue figures. However, I'm sorry, we put the sediment transport into that hydrological simulation. Sediment transport consists of the sediment rolling under the river, and it consists of suspended road and rolling stones in the river. So by calculating that sediment transportation, we put that term of the sediment concentration and speed of erosion and deposition from the riverbed or the slope. So this figure shows our result by using DRS-IRS. This is developed by our researcher. It consists of shallow water equation and transported sediment in the river, reduced discharge capacity, and lead overtopping river water to generate flood disaster. So the background green shows the mountain, and blue color to red color shows the water depth. And so basically, this area, this straight line-shaped water is river, and that light green color shows alluvial fan, the town we are living. And basically, the water comes into the river, but here the water inundate to the town. So it is our inundation simulation. So it was calculated the area of inundation. Then we want to show the area of inundation is always similar by calculating the ensemble simulation of hydrology. Basically, for calculating the sediment transport from the mountain to the alluvial fan, we have to set the starting point of the sediment happened. So it means that this is the slope failure in the natural mean. So we set that starting point by putting the data observed by the expert. However, once we change that starting point like this figure, I'm sorry, it doesn't move. So once we change that starting point randomly by conserving the number of the slope failure, then we calculate the hydrological simulation by using each starting point. Then we can get such kind of standard deviation divided by average to water depth. So this is coefficient of variation of maximum water level. And so CV, coefficient of variation around the outlet of the small catchment, like here, was 0.5 to 1. It colors red to yellow. This color shows the landslide location is relatively large. Change of the landslide location is relatively large for the predicted damage. So the time by time or the change of the slope failure, they change the devastated area. However, in the downstream of the alluvial fan, coefficient of variation is 0.1. It shows blue, like here or this area. So the location of landslide has a small effect for the predicted damage. So it means that if we do not know the exact location of the landslide failure in the mountain, we can predict the damage in the town because our society is we live in the convenient and comfortable place. And that means our living area topographically and numerically concave. So if we consider our probabilistic approach as the probability of magnitude of hazard to the probability of damage in each area, we can predict the damage time by time. So we do not know when and where disaster happens, but we know by simulation what happens when disaster happens. Then we put this kind of simulating technique into the machine learning. So basically, for disaster expert, they want to use the satellite image. This is the pre-disaster image, and this is the post-disaster image. And so by supporting that satellite image, they use the DEM. So this lady, I assume that this lady is an expert of the disasters. She wants to know the devastated area and damage estimation for quick countermeasures. And that requires the water level and sediment amount just after the disaster happened. And basically, she wants to know, wants to use that pre and post disaster and change them to the binary image of the difference between them. But if she is very skillful person, but she couldn't make such a water level and sediment amount estimation easier. Therefore, we want to help her by using the machine learning. However, machine learning requires training. So if that machine learning identify this is ship, we put many kinds of the photo which is ships. These are ships or these are airplanes and automobiles by annotating them. So by making the training, we can that machine learning can identify this is ship. But unfortunately, the disaster happened less frequent. Therefore, we need to make the data of the training by simulation. So we did that by using the K-computer, and we apply that kind of system into the Fugaku. So the strategy is here. So we develop, we put the DEM and land use, and we set the parameter randomly, changed to simulation by simulation. Then we simulate the maximum water level and the topographic deformation. And that numerics is kept. Then we binarize the change of the topography as a satellite image. So we annotate that binarization and the maximum water level for using the training. And so we train the deep learning. Then after the disaster happened, we put the image and binary image. Then that deep learning can calculate the topographic deformation and the maximum water level within very, very small time. We assume that the time between the disaster happened, I mean the satellite image taken, to the maximum water level and these kind of calculation within 2 hours. And Dr. Yokoya, who is an expert of machine learning, we established the cooperation between the AIP and the R-CCS. He's in AIP. And he uses the attention unit, this kind of network of the deep learning for picture identification and LinkNet as well. Then this is the result of our research. This is the satellite image difference between pre and post. So this is the input data. And we simulate or get the topography deformation by deep learning and inundation area from the deep learning. And this is the actual disaster happened in 2018. Therefore, we know the inundation and topographic deformation manually by expert. So we can compare them. Some of them are good and some of them are not good. So this is the final page of our presentation. This is the numerics of our result. As I mentioned, our simulation gave a good result, even just averaging the simulation of, for estimating the water level and topographic deformation. And RMSE is a root mean square error, so smaller RMSE is better. Intersection of the union is that is explained by this figure. So IOU is calculated by true and false, true divided by true and false. So it means that the bigger IOU is better. So in Northern Kyushu case, our original system, just a calculation and ensemble calculation, gave somehow better result. But by using the deep learning, we can build much more better calculation in terms of the water level and the topographic deformation. So this is the end of my talk. Thank you for your kind attention.